Hello everyone, my name is Zamir and I am going to discuss breaking the 2 to the n barrier for 5 coloring and 6 coloring. Actually, the result is more general than that, but we will slowly get into this. So first of all, let's take a step back and talk about what are we even discussing. So we are going to discuss exact algorithms for NP-complete problems. So obviously, many or all of us believe that NP-complete problems should not have efficient algorithms. Furthermore, we even believe that for many of these NP-complete problems, the best exact algorithms should be exponential. This comes in many popular conjectures being used for conditional lower bounds, for example, the exponential time hypothesis or strong exponential time hypothesis, and so on. But nevertheless, there are many NP-complete problems that have non-trivial solutions, even if these non-trivial solutions are still exponential or not efficient. And in fact, we were even aware of such better solutions for NP-complete problems before the definition of what NP or NP-completeness is. So already in the early 60s, there were non-trivial exponential algorithms for problems like the traveling salesman problem. After we defined the formal notion of NP-completeness and the community understood the importance of these problems, obviously we had much more work being done towards these problems. So nowadays we have non-trivial exact algorithms for almost every NP-complete problem you can think of. And maybe the most classical example, so we will spend a few slides on that one, is the problem of satisfiability, usually abbreviated to SAT. So this is the problem where you are given a Boolean formula and you need to decide whether or not it is satisfiable, whether or not there is some assignment to its Boolean input variables such that the Boolean output of the formula would be the truth value. And a more restricted version of this SAT problem is what we usually call K-SAT. So this is the same problem, except that now we restrict how the input formula must look like. So now the input formula is not a general formula, but a formula that is given in a KCNF form. So what is KCNF form? So a CNF form is as follows. You basically have a bunch of clauses separated by logical AND gates, where each clause is a bunch of literals separated by logical OR gates, where each literal is either a variable or its negation. So a formula in this form is called a CNF form formula, and a KCNF form is the same thing, where we also add a restriction that each clause contains at most K literals. So in this example, what we see is actually a free CNF form formula. And what is known about this more restricted variance of the SAT problem is that for every K that is larger than 2, this is still NP-complete. So for example, free SAT is NP-complete, and we were actually aware of that since the very beginning. So this is part of the first paper about reductions within NP. Nevertheless, for K which equals to 2 SAT is polynomial to solve. So we do have a polynomial solution for 2 SAT, but for every larger K, this is NP-complete. And now, okay, and now we can discuss what can we do. So we said that these things are NP-complete, but what still can we do in order to solve them? So the very naive solution for either SAT or any of the restricted version is to just do a full enumeration, full exhaustive search. You can just go over all possible assignments of binary values to the n input variables and check whether one of them satisfies the input formula. And this takes roughly 2 to the n time. I'm ignoring now and throughout basically the entire presentation any sub-exponential factor. So let's forget about the time of actually assigning the values and so on. So the very naive solution takes roughly to the end time. And there are non-naive solutions for SAT, but they improve the running time only by a tiny bit. They improve the running time by a sub-exponential factor. So actually, we don't know how to solve general SAT exponentially faster than 2 to the n, and many people believe or conjecture that this should be the case, that this is the best you can do. This is what I mentioned before, what's called the strong exponential time hypothesis. Nevertheless, for the more restricted versions, you can do better. So for every constant k, you can solve k-SAT exponentially faster than the naive 2 to the n. So for every constant k exists some epsilon k which is positive and obviously depends on k, such that you can solve k-SAT in 2 minus epsilon k to the n time. And we knew about such results since the mid-80s, and these constants epsilon k were improved many times since then. Okay, and with that in mind, we can go back to another quite fundamental problem within this NP completeness regime, and this is what we are going to focus on for most of this presentation and work, and this is the problem of graph coloring. So in the problem of graph coloring, we want to determine whether or not graphs are colorable with this and that amount of colors, or what is the minimal number of colors you need in order to color a graph. So let's begin with a quick reminder. We say that a graph is k colorable if we can color its vertices with k colors. This means that we assign to every vertex a color, let's say a number between 1 and k, such that no edge is monochromatic. This means that no edge connects two vertices that were assigned the same number, that are colored by the same color. So if we can do that with k colors, with numbers between 1 and k, then we say that the graph is k colorable. And the general graph coloring problem is to compute the coloring number or chromatic number of a graph. This means that you are getting an undirected graph and you want to compute the minimal number k such that this graph is k colorable. But as before, we can still talk about the restricted versions. So for every k, the k coloring problem is the more restricted problem of just determining whether or not this graph is k colorable for a specific for this specific given k, and not just computing this coloring number. And the general graph coloring problem is again NP complete, and again this is part of the first paper about reductions within NP. And again, in a fashion very similar to what we saw with SAT and K-SAT, for every k which is larger than 2, the k coloring problem is NP complete. Determining whether or not a graph can be colored using 3 colors is NP complete. But for k equals 2, this is polynomial. The problem of 2 coloring is the problem of determining whether or not a graph is bipartite. So this can be done very efficiently, but for every larger k, we can't do it efficiently. So far we are looking somewhat similar to the case of SAT and K-SAT, but now we are going to see a big difference between the two. So what is this difference? The difference is that in the case of SAT and K-SAT, the exhaustive search algorithm always took 2 to the n time. The size of the solution space, the size of how many assignments we need to check, didn't change as k grew. It was always 2 to the n. We always add just n binary variables to assign values to. Nevertheless, in the case of k coloring, the size of the solution space grows with k. So the naive bound for k coloring is actually k to the n, because I have n vertices and every vertex can be colored with k colors. So this depends on k and grows with k. So on a first glance, it is not even clear that you can solve the general coloring problem in exponential time that does not depend on k. But this is not the case. In 76, Lawler was the first to suggest a very simple dynamic programming algorithm that computes the chromatic number of a graph in roughly 3 to the n time. Again, I might leave out some exponential factors. And this is in fact very simple. So how do you do that? First of all, we notice that a graph being k-colorable is equivalent to saying that the graph can be partitioned to k independent sets, right? Because every coloring class is an independent set. Every set of vertices that got every specific color are an independent set because they don't have any edges between vertices of that color. Otherwise, this would have been a monochromatic edge. So now we can use that to peel off independent sets and get a very simple dynamic program. So how would the dynamic program look like? We will just go over all subsets of vertices, let's say by ascending order of their sizes. And now we will compute the chromatic number of the induced subgraph on that subset of vertices in the following way. If that subset of vertices is just an independent set, then we can color it with one color. This is our base case. And if it is not an independent set, we can go over all independent sets within it and color it by one new color for that independent set and how many colors we needed for the rest of the graph. So we basically peel off one independent set and the rest we just use the dynamic program to compute, and we just take the minimum over all choices of independent sets. So this thing would give us the chromatic number of every induced subgraph and in particular of the entire graph, and you can verify that this takes 3 to the n time. And this thing was improved many times by many different very interesting ideas until all of this work accumulated in 2009 in a paper of Bjorklund, Usfeld, and Kuivisto, where they obtained a 2 to the n, again, up to sub-exponential factors, algorithm for computing the chromatic number of a graph. So now again, we are getting more similar to the subcase. So 2 to the n is enough to compute the chromatic number of a graph regardless of k. And actually for several reasons, many people conjecture that this should be the right answer, that this shouldn't be improved further than that. This, even before this result, this is what people conjectured the holy grail of this type of algorithms should be. So far we are back to a picture that is similar to what we had with SAT, but now we need to ask ourselves what happens with k coloring for fixed k, for any constant k. Can we again improve that for every value of k? So the situation was as follows. So as we said, the general graph coloring can be solved in roughly 2 to the n time. And it was known that free coloring can be solved faster than that. It can be solved in roughly 1.33 to the n time. And that 4 coloring can be solved faster than that. It can be solved in roughly 1.73 to the n time. But here things got stuck. Unlike the case of KSAT, for every k that is larger than 4, the best known bound was still this general 2 to the n, which is somewhat interesting, right? Because it made sense beforehand that for any specific k you can get something that is exponentially faster, but here it seems to get it stuck at some point. And this leads to maybe the most interesting open problem in this field that we don't answer completely, but we go towards answering it, which is, should this be the case? Should there be some k in which we get stuck, or should we have some exponential improvement over the general 2 to the n for any constant fixed value of k? So what we show is the following. So first of all, we show that 5 coloring and 6 coloring can also be solved exponentially faster than 2 to the n. So we push this a bit further. It's not only 3 and 4, but also 5 and 6 that can be done substantially faster than 2 to the n. But much more interestingly, we show this using a much more general statement, which I will now explain. So we use the following statements to get the 5 and 6 coloring results. We actually show that in general, K coloring for general K can be solved exponentially faster than 2 to the n for a very large, very general family of graphs. So what is this general family of graphs? We show that for every positive delta and alpha, there exists some positive epsilon that depends on them, but on nothing else. It does not depend not on K, not on n, obviously, such that we can compute the chromatic number of the graph in 2 minus epsilon to the n time, as long as the graph contains at least alpha fraction of vertices that are of degree that is at most delta. So this is basically saying that if you have at least some constant fraction of vertices that have degrees that are bounded by any constant, then you can get an exponential improvement over the general 2 to the n for even computing the chromatic number. And this result is obviously more general than just looking at K, which is equals 5 or 6. But using this as the main building block, we managed to get the general result for 5 and 6 that does not require any constraints on the structure of the graph. And this generalizes previous results for things that are much more restricted, like bounded degree graphs, for example, in which there were similar results. Okay, so in the rest of the talk, I'm going to give you some high-level rough overview of what we do in the paper, but as our time is quite limited, I'm going to focus mostly on a part that I think might be the most useful for other things. So what do we have in the paper? So the paper basically consists of 3 parts. The first part is the part in which we prove this more general result, in which we prove that for every delta and alpha, you have this epsilon such that for graphs of that type, you can get an exponential improvement. But in order to prove this thing, we use a new combinatorial result. And this is what I'm going to focus on for a bit longer, because this might be useful for other things. This is somewhat more general than what we need for this result. This is some subset removal lemma that we are going to discuss in a bit. And the last part is using this more general result as a building block for a reduction between K coloring and K minus 2 least coloring. So this is basically showing, using this epsilon delta alpha result, that if I can solve K minus 2 least coloring, which is a slightly different problem, in time that is exponentially faster than 2 to the n, then I can also solve K coloring in a very similar time to that. And in fact, the results that had exponential improvements for 3 coloring and 4 coloring were also true for least coloring and not only for regular coloring. So this means that the algorithm we mentioned beforehand, solving 4 coloring exponentially faster than 2 to the n, using this reduction, translates to an algorithm solving 6 coloring faster than 2 to the n, because we can lift 4 least coloring to 6 coloring. Okay, and what I'm going to do now is, again, because of time constraints, not focus on the proof, but I am going to spend a few minutes discussing the statement of this removal lemma we are using. So what is this removal lemma for small sets we introduce? And this is the main combinatorial contribution maybe of the paper. We show that if you have some collection F of sets such that all sets live in some universe of elements U, and every set is of size at most delta. This is what we call a delta set here. So again, I have a collection F of sets. All of the elements in the sets live in some universe U, and every set is of size at most delta. And other than that, I also have some arbitrary positive constant C. Then I always have the following structure. I always have a subcollection F prime and a subset of the universe, from which the set elements are taken, U prime, such that the two following conditions hold. So the first condition is that for every two sets in the subcollection, for every F1 and F2 in F prime, the intersection of these two sets is completely within this subset of the universe U prime. The right way to think of that, the way we think about this thing, is that after I remove all elements of U prime from a universe, if I take this set U prime and just make it disappear, I remove it from every set in my collection, I remove it from everywhere, then the collection F prime becomes mutually disjoint. Every two sets in F prime are completely disjoint, except of some intersection within U prime. So if I ignore U prime, the collection F prime becomes mutually disjoint. And the second condition would be trying to say that F prime is very large, this is still a very large collection, but U prime is very small. So what is the exact statement? The exact statement is that the size of F prime is at least some function rho of delta and C. So if both of them are constant, this function will give you a constant as well. This function is positive for every input delta and C. So we have this constant times the original size of the collection times the size of F, and we add to that some this arbitrary constant that you picked times the size of U prime, times the size of the subset of the universe we had to remove. So basically this means that the subcollection F prime is at least in a constant fraction of the size of the original collection F, but furthermore, the size of F prime is arbitrarily larger than the size of the subset of the universe I need to ignore. So this means that I can pick C as large as I want and have this collection be so much larger than what I am deleting. And this removal lemma is very helpful in this regime of exact algorithms, because it kind of lets us take only it lets us to take something like a collection of sets that are general, a collection of small sets that are not necessarily disjoint, and make them completely mutually disjoint just by making a few universe elements disappear, which means in that case, and maybe in any other use you can think of in exact algorithms, we can just enumerate over some of the elements. So we can do something expensive for this small subset of the universe that we want to disappear, and we would be able to afford that because the collection we are getting, the collection that will become mutually disjoint after this deletion, is much, much larger than what we had to do. Okay, and I will finish with saying a little bit about this reduction from K coloring to K-2 list coloring, but actually in order to make it simpler and quicker, we will show reduction only to K-1 list coloring, because the reduction to K-2 coloring is much more involved. So first of all, what is list coloring? So K list coloring is the same problem as graph coloring, except that now each vertex has still only k options for a color, but these k options are not necessarily the numbers between 1 to k, but they can be any general subset of k numbers, of k colors. So here is an example. This is an example of free coloring. Every color is given some list of 3 colors, and it must choose a color out of that list, but the lists are not necessarily the same. So k coloring is a special case of k list coloring, where all of the lists are exactly the same, or just all the colors between 1 to k, for example, but in k list coloring they can be different than each other. Okay, and how do we reduce k coloring to k minus 1 list coloring? So we notice the following observation. If my graph has almost all of its vertices, let's say 1 minus alpha n vertices of degrees that are large, let's say at least delta, then this graph must contain a very small dominating set. What is a dominating set? This is a set of vertices such that every vertex not in this set has at least one neighbor within this dominating set. So even if you just take a small fraction of the vertices randomly, let's say roughly this amount, then you are likely to get something that touches most of the graph. Why? Because for every vertex that is not in this alpha n vertices that are of small degree, you have delta different neighbors that you might have picked. So if I have delta different neighbors that I might have picked, picking something like ln delta over delta fraction of the vertices should be enough to hit at least one of them. And whatever I didn't hit, this small fraction I didn't manage to hit, I will just add it to the dominating set. So if alpha is very small and delta is very large, then I get a very small dominating set that touches everything else in the graph. So if we are in that case and we have a very small dominating set, then we can solve the problem easily. How can we solve the problem easily? First, we will enumerate over the colors of vertices within the small dominating set. And after I have the colors of things in the small dominating set, I can notice that every other vertex in my graph doesn't have k possible colors anymore. It has only k minus 1 possible colors, because I already colored at least one of its neighbors. So it has one color less. So the problem that I am left with is k minus 1 list coloring. So if I manage to find a small dominating set, I can pay a bit for enumerating over the colors of the vertices in the small dominating set, and then my problem is reduced to the problem of k minus 1 list coloring. So if I could solve k minus 1 list coloring exponentially faster than 2 to the n, then in that case, I could also solve k coloring faster than 2 to the n. And now the thing that is left to notice is that in the other case, our general result solves the problem itself. What do I mean by that? Let's pick some large constant delta and some small constant alpha, such that if I am in the case that 1 minus alpha fraction of the vertices of degree at least delta, then I can indeed do what I just mentioned and get an exponential improvement. And then if I can, then everything is fine. But if I can't, it means that there are only, there are at least alpha fraction of the vertices at f degree that is at most delta. But if this is the case, then I have an exponential improvement using our general result. Because if I have some constant, any constant alpha fraction of vertices at f degrees bounded by any constant delta, then our previous result already gives an exponential improvement. So I'm sorry for being a bit quick with that, but this is the simple reduction from k coloring to k minus 1 list coloring. To go for k minus 2 list coloring, you need some more involved mechanisms, because the same idea is not enough, because it could be that even if I hit many neighbors of some vertex, all of them were colored with the same color or something. So it doesn't mean that the color list will keep getting smaller and smaller, but K-2 list coloring is also possible with a bit more complicated algorithm. And this is most I wanted to say, but obviously we are still being left with this open problem, this major open problem of whether or not K coloring can be exponentially improved for every constant K and not only for K up to 6. And this remains open, and any progress on that will be very exciting. Thank you very much for listening. I hope anyone is listening, and I will see you in the Q&A session during the online conference itself.